maximal leakage. And I covered the basic definition, the basic theorem, variations on it, comparison with mutual information and maximal leakage and differential privacy, etc. I did not really say much about mechanisms, so I'm going to take maybe about 10 minutes, 15 minutes maybe, and talk a bit about mechanisms. So we've tried applying this in a few different contexts. One kind of meta theorem, if you will, that's come out is that the metric tends to favor quantization over, say, adding noise. It's not an absolute statement. Okay, it's not always the case that's the way to go, but we have various theorems that in certain situations it's what you want to do. So I guess I put up one kind of trivial example of that yesterday. I was going to do a slightly less trivial example right now. So it's just a comment on optimal mechanisms. So let's consider choosing py given x to minimize the leakage subject to an average cost constraint. Okay, so suppose you're given the distribution for x. So the leakage itself is kind of invariant to the distribution for x, but when you talk about average cost, obviously the distribution for x then appears. Suppose we're given that. Suppose we're given a cost function C, which would just take an x symbol and a y symbol, and would map that to a cost, and we will allow infinite costs. Okay. And then I can imagine minimizing the leakage over all mechanisms. So I guess we're fixing the y alphabet here as well. So think about the x alphabet is fixed, the y alphabet is fixed. That's my attempt at a calligraphic font. So the two alphabets are fixed, and the marginal for x is fixed, and we're given a cost function. And now I can imagine trying to minimize the leakage from x to y, subject to a constraint, say, on the average cost. So I want the expected cost to be less than or equal to capital C. Okay. All right, so that's a problem you can write down. It's kind of convenient for computational purposes to eliminate the log in here. So this has an implicit log. So we'll use the computable characterization right here for this. So it's helpful to eliminate the log. So I'll just take 2 to the power that. Okay, and then it means you're minimizing over the mechanism of sum over y, x over x. Let's suppose it's full support, in which case you don't need that condition to be carried along with this, right? Okay, so this you can write as an LP in your program. All you do is kind of define extra variables that capture the column sum, and then it's all linear in those variables. Okay, so in general, I guess you'd stop there and say, okay, that's the problem. Given all this stuff, you compute the LP, and that's that. We've tried applying this in some situations like the RSA decryption side channel I mentioned yesterday. So the decryption takes a certain amount of time. You want to kind of delay it, possibly randomly, a certain amount of extra time before you announce the result to make it hard for an adversary to conduct these kind of timing attacks. And one apprehension we had about applying this result there is that my computer architecture colleagues want to measure x at almost like an instruction level granularity. And so the alphabet for x ends up being really big. The alphabet for y ends up being really big. So yeah, you can solve this LP. In principle, the LP is huge. It may or may not run in a reasonable amount of time. Even if it does, you've got this huge py given x matrix you've got to work with. You've got to store that. You have to kind of implement the randomness intrinsic in it, and every time you do the RSA decryption, so it's not clear this is really going to work. We solved this LP in some examples and found it had some structure to it. In fact, it looked like every example we ran, the py given x was always a mixture of at most 2 deterministic py given x matrices. And so we tried to show that. We were able to show it, although it turns out that there's structure in our cost matrix that was cropping up, and that structure is important. So let me show you the structure that was cropping up in our cost. So the cost function I'm going to view is a matrix. Okay, so the x are the the rows, the y the columns, like this. Okay, so an xy entry just tells you the cost. If the true computation time was x and you announce it at time y, then what's the cost? So the cost matrix that we had a certain property to it. It has infinities. In our case, the y has to be greater than or equal to x, so it's upper triangle and you have infinities beneath it. More generally, I'm just going to impose the constraint that if any one entry is infinity, then everything to the left and everything below is infinity. So the infinities kind of form a staircase like this.
So is that some kind of causality?
Yeah, you can think of it that way, yeah. Like y has to be greater than or equal to x, yeah.
Like in this case, you're timing things, right?
Yeah. X is so like this, everyone agrees on time 0 when the computation starts. X is the actual completion time, and y is the time when we announce the result. So y has to be at least x, which is what gives us infinities.
Right.
Yeah. And then also the finite entries are non-decreasing along the rows. Non-decreasing in that direction. Okay. So, in the actual completion time example, you'd have infinities, below the diagonal, and then it's tuplets after that. You may have zeros, on the diagonal, and then 1 on the super diagonal, and so on, right? So the cost increases the more you delay y for a given x, okay? So we'll call this staircase increasing, just for lack of a better name. So cost matrix is called staircase increasing if it has this structure to it. So if any one entry is infinity, everything to the left and below is infinity, and then the finite values are non-decreasing along the rows.
And
okay.
Does it matter that they kind of behave nicely along columns?
No. Decreasing along the rows, and infinities have to form the staircase. That's it. Yeah.
Just for the particular application, this RSA description thing, what are the range of what's the fastest decrypt? What's the fastest one and the slowest one, so that I get a sense of. I just wanted to have a sense of
Yeah.
How terribly leaky is it?
Yeah, I don't know numbers off the top of my head. We've been playing with some small examples.
In terms of orders of magnitude difference, or is it
Yeah, so we've been playing with some small examples, like 16-bit key, because then we can just exhaust all the keys and measure all the possible things. And for that, you don't get a huge discrepancy between the worst case and the fastest one and the shortest one. But it is there, and there's a reason why the computation is done. The results announced when it's done. To begin with, is that the average case is better than the worst case. But as you grow with the number of keys, I don't know how that scales. As the size of the key grows, that gap could open up. But yeah, it's a good question. Okay. So, so the theorem is, for this problem, for this LP, if the cost matrix has this structure.
So what is the size of x and y?
So it depends. We started with a 16-bit key example, and then I think the size of x and y were in the hundreds or thousands or something. But then when you have realistic size keys in this example, then it blows up to the alphabet size of hundreds of thousands into millions is what we estimate. You can't exhaust all the keys and even check it, so you're kind of estimating, but big. Big enough that the py given x matrix you can't really store even if you could solve it, right? But there's some structure though that we can use. Okay, so the theorem is if our cost function is staircase increasing, okay, then the Lagrangian of this is minimized by deterministic mechanisms. So for all lambda. Leakage, or the leakage without the log factor, plus lambda times expected cost. I'll write it like that. This is minimized by deterministic py given x mechanisms. So first, I'm not going to go through the proof of this. First, let me just say a word about the implications of this. We're happy to have this because it implies various useful things for us. For one thing, it means that what we have to store, the py given x object, is really like a 1D structure rather than a 2D structure, right? For each x, you just kind of store which y it maps to. You don't have to produce randomness in your mechanism, obviously. It's a deterministic scheme, right? You're not prone to averaging attacks because it's a deterministic scheme, right? So this kind of buys you a lot, and it's not something we forced ahead of time. I mean, it's nice to have deterministic schemes, and that just falls out of the math. It's what it wants you to do. You don't force it a priori. Our proof of this is like a lot more complicated than I thought it would be. Like when we first started seeing this, that like deterministic mechanisms were copying out of this LP, I thought, well, like if it's true that deterministic mechanisms are optimal, it should be easy to show, because like for this LP here, like there's an implicit constraint on py given x as a probability stochastic matrix, right? So the extreme points of that feasible set. Deterministic mechanisms are extreme points of that feasible set, and certainly like extreme points, should achieve should be one of the extreme points would be optimal, right? So something you can maybe kind of argue, oh, LP extreme points, it should kind of work out. Our proof is more complicated than that. The reason is that we have to argue that there aren't other extreme points that are not deterministic mechanisms, and that's kind of where all the work is. So we have this elaborate mass moving procedure given a py given x. We kind of move mass, along certain rows in certain ways simultaneously to make it more deterministic. We have a Lyapunov function that captures how deterministic it is that we argue is increasing, and so on. And yeah.
So Aaron, if y has a bigger alphabet than x, how can this be private in any way if it's deterministic?
Okay, so I'm skipping over that. Yeah. So we showed separately that under this formulation that there's no advantage to having y have a larger alphabet than x.
Oh, so you're using the fact that they collide into it's like injection of some kind, so that seeing y, you don't actually know which x led to it.
Right, it has to.
Even though it's deterministic.
Oh, yeah. Okay, I'm sorry. I was answering a different question. Yeah, I mean the py given x that you get, is going to look like something like that. Right.
So for every x, there's a deterministic y that you will.
Yes.
And therefore, y must have a smaller alphabet. Otherwise, by seeing y, I know exactly which x.
Right. Yeah.
Just looking at the matrix, does this correspond to something like, well, I'm going to just release things in batches once I've accumulated enough events, I'm going to...
I mean, it's a one-shot thing. We're not accumulating events.
Sorry, discretized too.
Exactly, yeah. So in my mind, this is basically what information theory we call a quantizer, is essentially what happens. So like your py given x, I'll draw it down here, your py given x, you have essentially like a set of allowable y's, right? And then your mechanisms are going to have zeros where there are infinities. And so given any row, given any x, all you do is kind of map it to the y that's allowable. That gives it the lowest cost. So you end up with mechanisms that kind of draw this very well.
So, but I guess the interesting phenomenon here is that even though you're allowing arbitrary kinds of randomization,
yeah,
maybe not arbitrary, but subject.
It's arbitrary. Yeah, right.
Subject to like causality.
Yeah, exactly.
Like causality.
Yeah.
Nevertheless, the best thing to do is to discretize.
That's right.
So
Yes.
I'm going to give you a corollary or a stronger theorem. So if you take away the expectation on your cost, this will always be true. And that's sort of what we showed yesterday for all maximal alpha leakages, including maximal leakage. If you don't have an expectation, if you have a hard constraint on every xy, this is always the answer.
Okay, so you're saying if this is not expectation, but if it's like for all xy like that, then by always true you mean you don't need this assumption anymore? Okay.
In other words, it is a deterministic mapping which quantizes.
Okay. Yeah. Could be.
So should I then interpret it as like I'm leaking h of whatever that partition is?
Yes.
It's about the key.
Right.
What's h?
Like
Entropy.
No, it's just log of the number.
Oh.
Right. But if I knew your mapping
Because
ahead
there's a
of
total
time,
probability.
So
If
I say put the uniform distribution on keys, right, then I would, like, there's a total probability that I delay in 1 second versus 2 seconds versus 3, suppose it's 1, 2, 3, 4 seconds. So then there's some sort of output distribution on seconds. I'm going to learn something about the set of keys. So
Yeah, I mean,
how would I interpret it in terms of, like, I mean, I guess what is the leakage? Maybe that's the right question.
what is the
What
leakage?
does leakage end up being in the?
It's log of the number of different values you have here.
It is. Okay.
Yeah, exactly what it is. Yeah.
Yes, another question is, how sensitive is the solution to p of x? Like, is it the same over a range of p of x's, or do you end up getting different?
Oh, yeah.
How is it sensitive to P of X?
Good question. I mean, there are only finitely many of these things, so it has to be insensitive on some level, right? But
Appears in the expectation, right?
yeah.
Yeah. This is different, yeah.
So, I mean, I'm just wondering if you change p of x, how would the solution
So,
change?
but I think Anand is correct. If I saw it after 1 second, I literally know that it came out of this X or that X. So that's my uncertainty, right? My uncertainty on a smaller set every time I see an output.
Yeah, I mean, a priori it could be any x, and then you observe y, and you know it's one of those. That's true. But I mean, this is saying like that form of muddying, x is preferable to one where you try to, like, say, add noise to it.
Right, but
It doesn't do that to it. I can add a geometric or something to it. Sorry?
Is the output distribution uniform?
Is the output distribution uniform? Not in general. It would depend on px.
Yeah.
Right,
Yeah.
so then that's why I'm saying it's like a little unclear to me that you would then say, oh, you leaked, 2 bits in this case, if the output distribution is, say, is not uniform.
Well, okay. I mean, that goes back to, so we've
Or is it uniform? Sorry, if I look at if I sum up all the probabilities of all the x's corresponding to one value of y, is
Yeah.
that like 1/4 of the, would that be like 1/4?
that's basically asking whether y is uniform.
Yeah.
No, it's not in general. And I guess your question kind of amounts to, like, why do I formulate it this way? Why don't I put mutual information here?
No,
I
I'm just trying to understand how much I learned about the key, that's all.
All right.
Yeah. Okay. So if
I don't believe that I learned 2 bits about the key. So, yeah.
I mean, if we adopt this, notion as the measure of leakage, then we'd say you leak exactly 2 bits from x to y. The key is one particular s.
Right.
Okay. So the probability that the adversary can guess s after observing this is upper bounded by.
The key is not x, right?
Yeah, the key is not x. That's true. The key is the time. The key is the actual execution time. I'm sorry. X is the actual execution time. It's not the key. Okay.
I think the idea is because you're just suppressing all functions, and therefore you're suppressing this S, and the most you can leak is really 2 bits, right? It could be lesser, but it's an upper bound metric.
Right,
What
yeah.
Maximal defines it as.
I mean, there exists an S that it is like exactly 4 times easier to guess correctly than it was before. That may or may not equal your key. Actually, it kind of does in this case because the key is uniform and X is a intrinsic function of it. But that's a throwback to last lecture. Okay, so anyway, our proof of this is more complicated than you might think. In defense of our proof, I'll just mention that some assumption like this is necessary. So you can't delete this, and so you can check that this conclusion is false if you have a simple circulant cost matrix like that. Then it will it'll settle on a random scheme, not a deterministic one. So any improved proof that someone has to use something like this structure, and it is not just a matter of saying, oh, LP,
What
that's
if it's
that.
symmetric? Like, what if releasing, obviously the causality is a problem here, but like,
Yeah.
if it were equally problematic for me to release early as it is to release late, then, like, if underestimating and overestimating had the same cost, would you get a different
symmetric.
structure if it was symmetric?
Yeah. So like if it was symmetric and
Symmetric,
toplets,
yeah.
you're asking does the theorem hold if C is symmetric and toplets? Is that the question?
Probably that's what he's asking.
Remind me what toplets means, identical on the diagonals?
Yeah, the diagonal entries are all equal, the supers diagonals are all equal, yeah.
Sure. Let's start with that.
Yeah.
It might be true.
Yeah, I don't know. I mean, that's toplets and not symmetric.
That is true.
Yeah, that one's like a little weird because
But it's
the
not
twos,
symmetric.
Yeah, the 1 and 2s are flipped. Yeah, I agree. Yeah, I don't know.
Okay.
I don't know. All right. So last point is you can just compare this with what you get with other metrics. Okay, so let's suppose our cost matrix do like a 4x4 example with that structure.
Sorry, Aaron, just in your theorem, you still have to assume that y has a smaller alphabet, right? Otherwise, it's not true. Is that the one?
No, you could do it with an enlarged alphabet.
Really?
Yeah.
Wait, but then given y, oh, it's just you don't care then? Because then given y, you can perfectly construct x every time, right?
I think you don't need a large.
Well, no, I mean, it's just going to try to minimize leakage. I mean, it depends on lambda, of course, but I mean, part of the goal here is to minimize the leakage. So,
Same symbol.
yeah, I mean, you could map, if x and y have the same alphabet, you could map x to y. That's the identity py given x. So that's a feasible point. It's not going to score well here. I guess it would score well there. So now it's going to.
Because you're also not putting any assumptions on what you can pick for a roll of a p of y given x.
Right, yeah, anything is allowed. I mean, it's baked into here with the infinities, basically, is capture what's allowed there. So yeah, I mean, I guess if lambda was really, really big, then this scheme would find the identity matrix for py given x, and that would, that would make this big, but you don't care because it's all about minimizing the cost.
Yeah. So that's worried about. Let's wait and see.
Okay, so I'm almost done. So suppose you want to minimize the cost, subject to the max leakage being less than or equal to 1 bit, or in place of this, you could do mutual information less than or equal to 1, or in place of this, we could do local differential privacy less than or equal to 1. Okay, so different forms of the same problem. Suppose I'm allowed to leak one. I've kind of flipped it around here, the objective and the constraint. Okay, so under maximal leakage, the optimal mechanism for this cost matrix and this leakage constraint, it's 4x4, and it's like that. Okay. Anything else is 0. It's consistent with that. That leaks log of 2 bits of information.
We are randomizing.
Yeah. Py given x. They all have to be upper triangular, right? And it's just a dense matrix. It's just stuff. It's just numbers, numbers between 0 and 1. Okay, so it's a full randomizing thing. So this is a lot easier to implement than that, right? Because you got to store the whole matrix. You have to implement real randomness when you run it. Local differential privacy.
Beautiful.
So for local differential privacy, there exists one mechanism that gives you finite cost and finite leakage. And it's just wait everything, delay everything until the worst case time, and then release.
Oh, because of the causality constraint.
Yeah, because of the causality constraint, right? So if you try to move a little bit of mass from here, to the left to try to get your cost down, you got to have a 1 here, otherwise the leakage blows up to infinity, and the causality prevents you from doing that. So for this particular application, like local differential privacy, it really gives you no trade-off at all. There's only like one, allowable solution, and that's it. These ones at least allow you to kind of trade off the two, but this one's arguably easier to implement.
But
Certainly, I would argue maximal leakage is capturing what you care about in this application, but this is added bonus. Okay.
I have one more question. Like, yeah, the mechanism looks easier to implement, but is there an easier way to solving the optimization problem?
Is there what?
Like, the mechanism, it turns out to have a simple form.
Yeah.
But solving the optimization problem might still be hard, right? It might still require searching over.
Good. Yeah.
So is there like a clever algorithm for optimizing?
So you can leverage this a bit. So if you want the trade-off, like between the cost and the leakage, now this thing is going to be piecewise linear, and the kink points would only be at integer values of the exponentiated leakage. So you only need to solve at those points, first of all. And you also know that you only really care about deterministic mechanisms. So we have studied like greedy algorithms that kind of start with this, and then they look for like what's the single best column to add to get my cost down, and then given that column, what's the single best column to add to that, and so on. And so you can kind of build up schemes that way, and it's a submodular thing, and so you can get like a 1/e guarantee compared to using the LP.
Must be able to get like some reasonable polynomial time of dynamic
Yes.
programming here, right?
You can just run the LP.
LP is polynomial factors, so.
No, but like, I mean, like n squared, right?
Oh, okay.
Just, but by the fact
Oh,
that
yeah.
if I'm
Sure.
putting a release point at time t, and I know there were k release points before that, I can separately solve the two optimization problems. I don't really have to worry
Right.
about where those are versus, there's like a, recursive structure to this problem. Smells like the kind of thing that shows up in, classic dynamic programming.
Possibly.
Not not what like electrical engineers call dynamic programming, what computer scientists call dynamic programming.
I didn't know there was a difference.
Slightly different.
Okay.